going to write about a ring buffer, an array-based buffer with efficient access at both ends. We completely foreshadowed this, and we're going to see how it goes. If you're in the Rust world, your main access or interaction with a ring buffer that you didn't get from an external crate or implement yourself is probably going to be the VecDeck. VecDeck is a growable ring buffer. We're not gonna implement a growable one. We could, but we're not going to. We're just gonna implement one with a static size, static capacity. Nice, AOC and Zegjon, that's great. Okay, so ring buffer. In the last article, we faced the limitations of the array list, namely that operations at the front are costly. Okay. A ring buffer also known as array buffer, circle buffer. What else do we have? Also known as array buffer or circle buffer. It is funny, like array buffer. Like you have no idea that this means it's like it's circling around. Do they ever call it a circle array? Is this the blocked Dylan from Milroy fan club? Yeah, exactly right, Kyle. Oh, Capital One. You guys know that I have a Capital One account. Ugh, terrible. Circle array. Let's try circle array and see if anything comes up, John. I mean, sure. Is it not the same thing as a ring buffer? What's up, Brian? Circle array versus ring buffer. Is it the same effing thing? Circular buffer. Okay, let's go here. Circular buffer, circular queue, cyclic buffer, or ring buffer. All right, we'll just go here. Okay, we'll just stick with what we have. I thought you needed a synonym to clarify. No, but I was curious based on our prior conversation. Like, is there something that is like, do they actually call that? It seems like a circle array is potentially something else, but who knows? Or simply not a term that's used. It's my favorite JS on the server person. Tech support just earned himself a block from Ryan. A ring buffer, also known as array buffer or circle buffer. That's good enough. Maybe also known as an array buffer, sure, or circle buffer. Gives the provides access to both sides of a sequential series of data Okay. Provides access to both sides, provides constant time access to both sides of a sequential series of data while using a contiguous memory. I don't want to say buffer again. I mean, it's kind of the point is that, maybe that is the point of the name after all, is that we have a contiguous memory buffer. I don't know. A series of data while using a contiguous memory, I could say block. Let's say allocation. Allocation or buffer, wink, wink, underneath. Now, somebody might come in and be like, that's not why it's called that, but I don't care. WWDC. Nice. Thanks for the lurk, Ryan. I appreciate it. Speen, what's up? I think when I did this in my DSA class, it was in the same unit as DQ, but used static array instead of linked list with pointers for the start and end, meaning it could wrap. Okay. Yeah. Yeah, so it is going to wrap, and I mean, we were not going to write the code today, but we'll probably like walk through it. You did the whole being an Apple fanboy thing. Oh man, we're really going for it with trying lyrical music today. So far I've survived. I don't know. I guess I just drown out all the other voices with my own. Okay. Underneath. Cool. I think that might be all that I need to say up here. And then we get into the actual implementation. Do I need to compare anything? Not really. So it's my really good thing here. Okay. Initiation party. Oh no. You drown out the voices in your head by learning Rust. Nice. Good plan, Scott. All right. A ring buffer uses okay. The foundation of the ring buffer is thus. I don't know. I guess I need to write out a little outline because the words aren't flowing. Maybe it is the lyrical music. I don't know. I really like this song, by the way. I'm not a whole Imagine Dragons stan, but I like this song probably because of where it's from. You know, it's a pretty good show. It was a pretty good show. They did a good job. All right. Ravek. Okay, so the point of a ring buffer, we have a contiguous memory buffer, aka it became so meme I hate it now. That's fair. I'm not cool enough to like hear about things all the time. Not in general text. I'm pretending that I can right now, and we'll see what happens. Usually I can't. But I'm so tired of the same music I always play that I wanted to try something different. If somebody has an instrumental playlist that, is more on the electronic or post-rock side, we can try that. I use Spotify. Send me a link. I don't know. Nice. Let's see. Contiguous memory buffer, aka raw vec based. Okay. Except we won't grow it. Okay. Okay, raw vec based, except we won't grow it. Forgot a U there. Nice. What else do we want to say about our ring buffer? It wraps around. I think that's the most surprising thing, right? Is that it wraps around. Our head is not index 0, and our tail index can be less than, in an absolute sense, our head index. I am probably just going to call it head and tail for my implementation, just to be a little bit similar to the other data structures we've done. RawVec is something I implemented myself. It's also used in the Rust standard library, Scott. All it really means is we have a contiguous memory buffer that we can optionally grow. Now, we are actually going to have to make some changes to our RawVec, where I can provide it an initial capacity, which of course you can do for like Rust stdlib data structures. But like, for instance, the only ring buffer in the Rust standard library, the vecdec, which is a growable ring buffer, is also based on rawvec. So it's just kind of an abstraction I stole from stdlib. Oh yeah, for sure. I can listen to lyrics that I don't understand. Spanish is not one of those, so I can't listen to music with Spanish lyrics. And then I'm getting close to where I can't listen to Japanese music because I'm thinking too much about what's being said. It wraps around. Our head is not index 0, and our tail index can be less than our head index. Hey, Sergeant Pepper. Ba, ba, ba. What else do we want to say? It overwrites optionally, right? It overwrites the oldest data with the newest. You know, it's not like you have to do that for a ring buffer. Some of them, they just fill it up, and they, once it's full, it's full. And then they might pull it to see if they can write new stuff to it. And typically functions as okay. It overrides the oldest data with the newest in our implementation. And then we can talk about use cases, right? Use cases. Anytime you want the latest n elements. Yep. I don't understand, Sergeant Pepper. Yeah, I already know Spanish. That's why I can't listen to Spanish lyrics. That's the problem. Anytime you want the last, latest in elements. It's probably more accurate to say that I used to know Spanish. When you don't speak something in let's see, 8 years, it's a little it's a little bit hard to be quite at the same level of fluency that you once were. At least for me. Anytime you want the last, latest in elements. Okay. I think this is good. Memory storage, we'll say memory constrained environments. So what are good examples of this? One is an undo. Undo redo can be a nice use of a ring buffer. Recent history. What's the other one? Not slow motion. Is it slow motion? Is that what I'm thinking of? Slow motion cameras, right? Slow motion cameras. Well, maybe I should say slow motion photography. Instant replay, stuff like that, right? Memory constrained environments, since it's fixed size. The scary cloth handheld machines and creepy old service stations. Oh no. That's so scary. I haven't seen something like that in a long, long time. Now there's also an interesting element of this, which I don't know if our implementation is going to handle correctly. But it's basically if you want what would be the right way to say this? Is it, I guess it wouldn't be synchronized, it would be I guess it would be async technically, right? Async. Let's see. Two processes sharing the same reader writer sharing the same buffer. Okay, I'll try to explain that better. I think this is good to start with. Maybe I can actually write some real words now. We'll see what happens. Okay. Ring buffer. We already said it has a contiguous memory allocation. The first thing we need for the ring buffer is a contiguous memory allocation. Thankfully, we already have one in RAVEC. We already have implemented one in RAVEC. And this will be a link to the RAVEC article. Which is here. In RAVEC. Okay, whoops, wrong one. Code. We need to do those up here too. I I think I'm gonna do this. Limitations. Okay, and then I guess since I said that, well, I haven't published the last article yet. Well, yeah, I'm still working on that. I was lazy and I didn't do it yet. We'll get there. I have to finish the benchmarks and actually like put them in the article. Okay. The first thing we need for the ring buffer is a contiguous memory allocation. Thankfully, we already have implemented one. Thankfully, let's take out already. We have implemented one in RAVEC. In RAVEC, while RAVEC has the capability of growing we just want a fixed sized allocation that is specified at initiation. Okay. This does require a few small changes to RAVEC over speed changes to the original implementation of RAVEC. Okay. This is fine. Okay. Last or latest. I know. Last/latest. You like that one? Isn't that good? All right. To the original implementation of RAVEC. Yeah, that's fine. I'm wondering if I just want to do that today because the ring buffer. Just thinking. I'm thinking. The ring buffer is really not that hard to implement. Fingers crossed. I don't think it's going to take me that long. So can I do the changes to RAVEC and implement the ring buffer in the same stream on Wednesday? I think I can. I don't think that's too much. I think we'll be okay. Yeah, you're right, John. Well, it's actually I% capacity, right? If you want to get technical. Yeah, you're not wrong, Patrick. This does require a few small changes to the original implementation of RAVEC. Okay, cool. This is fine. I don't know if this is going to be true, but I'm pretty sure one important element of specifying capacity one important element of specifying capacity is to use a power of 2. Otherwise, we can end up in some integer overflow issues. Some integer overflow problems. I don't know if I'm going to explain that more. I might just say, is there a comma after otherwise? I feel like there is. Otherwise, we can end up in some integer overflow problems. I don't know. Yeah, I definitely will actually you there, John. No doubt. Is there a nice article on the integer overflow problems? Why do we use... That way I don't have to explain it. Power of 2 for ring buffer capacity. I mean, if we're going to use modulo anyway, it might not matter, but it also depends on... Okay. It also depends on the implementation. Like, if we don't want to... So some people, when they implement a ring buffer, they will actually just keep incrementing right over and over again. They won't ever reduce it. And so you might have, 34 modulo 5, let's just say, right? So that's if you're using modulos. Now, if you're using masking, the logic doesn't actually work for bit masking unless you use a power of 2. So like, what's the one example I was looking at recently? It's something like this. We'll go into this interesting bad REPL because I haven't installed the much better REPL that exists. So if we take something like, this would be after a while, but still, I want to say it's this one. Let's say as U32. Okay, so if we have this nice number, and can't even control A in this REPL, unbelievable. And then we modulo, let's say our element is 17. We get 0. Now we would actually have to like figure that out. Is that actually correct? But the other example that makes it a little bit obvious that it's not correct is 38. And I think that doesn't work, if I remember right. Because of the way the overflow works. Now, this is just based on reading. I haven't actually done this in myself. So I don't know. I think this is true. Oh, here we go. But he doesn't. Let's see. I don't think this guy uses. He uses masking, so it doesn't actually explain it. Ba ba ba. Let's see. Bum 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 bum. Yeah, logical and computation in the following macros is a power 2. However, the system with the best size is not a power 2. Instead of a logical and, it is better to do a module computation that works with all buffer sizes. So maybe it doesn't matter if we're using modulo. I thought I read somewhere that it does. If the modulus is a constant power 2 and the operands are unsigned, then the compiler should use and. Okay, because I think we're just going to do it with modulo and not with masking, even though masking is like more efficient. Okay. Okay, so let's see. There are two main ways. Well, maybe this is for later. Our wraps around our head is not at index 0, and our tail index can be less than our head index. Okay, this does require a few small changes to the original implementation of raw-vec. Let's just say specifically adding a static with capacity, use size, method. How about we just say this? Forgot I can't use Markdown. Beautiful, beautiful. Specifically adding raw-vec, I guess I should say support for raw-vec with capacity, cap use size. Okay. Since we are using a fixed size ring buffer, what happens when it fills up? Okay. What happens when it fills up? It depends. For this implementation, we will continue to write data to the ring buffer. Keeping only the latest latest n writes, where n equals capacity. Okay. Where n equals cap. Okay. This is useful for use cases after all. This is useful for cases where retaining the latest in elements is sufficient. E.g. is sufficient. Let's see. A few examples include recent history, recent activity logs. Okay, I like that. Recent activity logs, slow motion photography, capturing only the last, say, retaining only the frames. No, this doesn't make sense. Okay, we'll just put these in here. Okay, a few examples include recent activity logs, slow motion photography, and undo, redo behaviors. Okay. For example, oh no. Did we die? Did the stream die? Are we back? My network's being kind of weird. No? Okay, I got scared. I got scared with the not like this. You're not a native English speaker, and you were like, use cases. Why are they use cases? How are they related to briefcases? It's funny. Okay. Oh, I think I remember where I read that. Should we look at that real quick? Where's I guess I just need to go to last closed tab. We'll go back. I think it is in this article. This one. Okay. If you replace masking with integer modulo size, you can use sizes that are not powers of 2, more expensive but handy if you really need a 17-byte ring. Unfortunately, I don't think that works. It needs to be a power of 2 or the integer overflow causes a discontinuity. Let's say we're using mod 17. The last slot before wraparound would map to slot 0 in the array. Increment it by 1, it wraps around to 0, which obviously again maps to... Oh, he's just talking about if you're using 32 bits. But if you're using 64-bit, right? Because the whole point is this. I'll just say that I and U32 max. Yeah. That's the point. But if we just use 64s instead, which in general I would just use U sizes. I mean, first of all, you would have to get all the way to this, which could matter in some situations, right? If you had like a long running thing. We're not even going to bother with this case. I really don't care. That's really the point. Like in what cases exactly my zero user? Well, this actually came up because of did you see the GitHub integer? It was actually the same thing as it was an I32 overflow on something. And I tweeted out basically what you just said, John. I said something like, this is why I use UUIDs for all of my apps that are never going to have more than 1,000 users. Yeah, good times. Yeah. So that's what he's taught. At least I just solved it in my head, right? We figured it out. Okay. Yay. I solved it in my head, aka I read something. Wow. Oh, I was like, wow, we've written a lot. This is not the right article. Okay. Let's see here. A few examples include recent activity logs, slow motion photography, and undo redo behaviors. Yeah, this is good. Not behavior, just behavior. Yeah, that's better. Okay. Sometimes yeah, let's see. Another option is to not allow, what would we call this? What is this called? Like, what do you call it when you've overwritten? Oh, overwrites. We could say, well, another option is to not allow data to be overwritten, and instead check if the buffer is full before writing. Okay. This is useful for cases where there are multiple processes. We'll say multiple. Let's see if this makes sense. This is useful for cases where there are multiple processes. There are, we'll say two processes. Two processes. Here we go. Where there is a reader and a writer process. And the writer has to wait for the reader to consume and make space for new writes. Okay. This is useful for cases where there's a reader and a writer process, and the writer has to wait for the reader to consume and make space for new writes. What's a good example of where this is useful? If something doesn't come to my head, I'm probably just not going to give. Like, this is useful for cases where there is a reader and a writer process, and the writer has to wait for the reader to consume and make space for new writes. Streaming video. Okay. Streaming video's a good example. Like, there's definitely ring buffers at work, right? Big text processing. Yeah. Oh yeah, basically just any kind of queue, right? Like any kind of queue in order to synchronize. Okay. Yeah, exactly. Yeah. So like an IO, let's just say IO. Yeah. An example of this is synchronized IO queue. Let's see. Is a synchronized IO queue. Where an example of this is a synchronized IO queue. Where the synchronization allowing the synchronization to... You were doing Q in an RTS game with it. Very fast to use an array. Cool. Yeah, thanks for that. That's super helpful. An example, that's where I got a lot of these. Like I honestly did not think about undo redo until who was it? Oh crap, I'm forgetting their name. They're on Twitch. They make, is it Funi Games? She told me about using undo redo. She uses a circle buffer in her chess game for undo redo. Is this for VecDeck or something else? It's just for my own data structure we're gonna write. Yes, discard. So yeah, obviously in the stdlib, vecdeck is the main case for, or the main place you're going to see a ring buffer in Rust standard library. We just want a fixed size allocation that is specified in allocate. Okay, where are we? An example of this is a synchronized IOQ. Allowing is an IOQ. Okay. What I'm trying to get out here. An example of this is an IOQ. Does it make sense to say that is synchronized at the memory level? Does that make any sense? Let me think about it. The point is that we're not having to check status using some state variable. We're literally just using the data structure, which is synchronized at the memory level which is synchronized by the data structure instead of external state, maybe. Processing real-time data is a nice example too. Yeah. Is an IOQ that is synchronized by the data structure instead of external state. Yeah. This can be used for real-time data processing. I like that. This can be used for real-time data processing. All right, example, this is an IQ that describes the set of external state. Well, it's not an example. That's what this is. Okay, an IOQ. How about used for real-time data processing? Okay, an example, this is an IOQ used for real-time data processing. And the point is that I want to see the ring buffer synchronizes. Okay. Maybe I don't care about this. Maybe that's too high level for me. I don't know what exactly mean for me, but like maybe that's not an important part of this. Like it's already kind of like it's a little bit grug focused, right? Is this fine? I think this is fine. I think this is fine. I think that's clear enough. All right. Let's just do this and we're ready to move on to the next thing. Since we're using a fixed size ring buffer, what happens when it fills up? It depends. For this implementation, we will continue to write data to the ring buffer, keeping only the latest n writes where n equals cap. This is useful for cases where retaining the latest n elements is sufficient. A few examples include recent activity logs, slow motion photography, and undo redo behavior. Another option is to not allow data to be overwritten and instead check if the ring buffer is full before writing. This is useful for cases where there is a reader and a writer process and the writer has to wait for the reader to consume and make space for new writes. An example, this is an IOQ used for real-time data processing. Okay, cool. I actually forgot to talk about vecdeck. We should probably just talk about it up here. Vecdeck in Rust's std collections. Maybe it's not in std collections actually. No, it is. It is. Maybe it's better just to say Rust's stood collections vecdec. I like that. Is a growable ring buffer. Is a growable ring buffer designed for general purpose use cases. Designed for general purpose use. Okay. Designed for general purpose use when designed for general purpose. Let's see. Let me read this preparing it. There we go. While most ring buffer implementations are fixed size. There we go. That's what I'm trying to say. While most ring buffer implementations are fixed size, Rust stood collections vecdec is a growable ring buffer designed for general purpose use. Okay, I think that's good. Wonder if torrent uses ring buffer. Yeah, I have no idea. 1 second. Let me do a quick message check. Okay, we're good. So we got this done. Hey, thanks for the follow, yes, Discard. I appreciate it. We're done quite a few data structures so far. And we will write the code for this on Wednesday. It wraps around our head is not index 0. And our tail index can be less than our head could be index 0, right? It could be. But then like what are you doing? What are you doing with your life if you start with your head at index 0? All right. Use cases, anytime you want the last, latest, and element. I mean, it doesn't really matter. Okay, we did all this. I like that. I like that. So we really just haven't talked about how it wraps around. Okay. I think this goes after this, actually. Unlike the vec or array list that we're used to, where the last element in a series of data will always have a greater index than the first. A ring buffer. Okay. Unlike the vec or array list that we're used to, where the last element in a series of data will always, okay, actually this is better, that we're used to. Let's see. A ring buffer, let's talk about it in a positive way. A ring buffer, the last element in a series of data can have a lower index than the first when using a ring buffer. Okay. Not bad. Not great, but not bad. Unlike the vec or array list that we're used to, the last element in a series of data can have a lower index than the first when using a ring buffer. Okay. The ring buffer. Okay. This is... Oh, yeah, that would be fun, John. Ring buffer and Weewa. APLs are wild. There's a guy who's in here a lot. Oh, God, I'm forgetting his username. It's what he gets for not joining the streams in the last couple weeks. Damn it. Anyway, he does a lot of BQN, which is pretty wild. Like a lot of BQN. Let's see. Unlike the vector array list, the last element in a series of data can have a lower index than the first when using a ring buffer. Let's use a little pseudocode example, and I think this might make this a little bit more obvious. Pseudo vec pseudo representation. I don't know if I'm going to keep it that way, but let's say we have 1, 2, 3, 4. I like sequential numbers because it just works. X represents unused capacity. We can visualize the difference between how an array list, we'll say array list since that's what we used in our actual library, between how an array list and a ring buffer utilizes the underlying array. Okay. I like this better. Array list and ring buffer. I almost forgot to do the actual thing that's helpful here. Okay. Cool. Of course, if I made it 8, it'd be at least a power of 2. I'd be like a nicer person, but it doesn't really matter. Okay. Array list. Ring buffer. We want a little white space. Does that make it a little easier to read? I think so. Okay. I think this is good. Unlike the vec or array list that we're used to, the last element in a series of data can have a lower index than the first when using a ring buffer. We can visualize the difference between how an array list and a ring buffer utilizes the underlying array. No. So you're right. Like this is pseudocode, first of all. We can visualize the difference, utilizes the underlying array. in this pseudocode. There we go. So the reason I'm not calling this an array is like we've already implemented an array list in this series. So it's a great question, by the way. And the point of the array list is the thought that we've allocated our raw vec, right? Our memory buffer or our array underneath. And maybe that's the point, is maybe I shouldn't say array here. Utilizes the underlying memory buffer. Sure. The underlying memory buffer in the pseudocode. Okay. Yeah, you get it. Okay, cool. No, I think that's a good point. And in general, I've tried to not call the memory buffer underneath an array because I didn't want people to get confused. So I think me using that word there did obfuscate some things. I actually think the visualization speaks everything that I need to say in this case, right? Obviously there's the logic for how we get to the tail. Okay. It may seem unusable in this form. It may seem unusable in this form, but the logic to calculate the actual... Really? Can I do this? You really just don't like anything that I do. Can I use Apple commands? Okay. It may seem unusable, but the logic to calculate the actual index into the memory buffer is simple. Okay. In the above example, the head is at index. I have to count. It's 6, right? Okay. Is at index 6, and the tail is at index 2. Is it okay, Shmeen? Good question. Is your example saying that the data starts like this or can be configured like that? It can be configured. Like this could be something that we end up where it ends up, right? So in general, we start with all x's, right? Like in general, those are zeros, right? Depending on our type and everything, but like usually these are just zeroed out memory buffers, right? So we start with all x's, and then when we push onto an array list, of course, we push 1, 2, 3, 4, 5, 6, right? Where our ring buffer, people do different things. Now you could start at index 0. Some people don't like doing that because you start to potentially lose the whole point of the ring buffer, which is that we want like quick access. But let me see. Does that make sense? Maybe that doesn't make sense. I guess that would just make sense on the... I was thinking of the growable one. Like, I have a hard time believing that vec_dec would start pushing onto index 0 because then, you start to lose the whole point. But maybe not. I haven't thought through that very well. But anyway, the point is you can start at index 0, but yeah, say you deleted some, etc., you'd be here. Yeah. Hey, William, what's up? All right, let me think about what I just said and see if it makes any sense. In the vec_dec growable ring buffer, does it actually make any difference if you started pushing onto index 0? if you have a capacity of 4 elements, you say 1, 2, 3, 4. And if you said push front, you could just push it onto the back. So it doesn't make sense. What I said didn't make sense at all. In the sense that, like, it doesn't matter. You can just start at index 0. But the point is, yeah, after some pops and some pushes, this is where we could end up. Yeah. In the above example, the head is at index 6 and the tail is at index 2. Okay. I don't prep for this very much in case it's not obvious. So I say a lot of dumb things, but it's okay. We figure out what actually makes sense at the end of the day. I think through it on stream, for better or for worse. It may seem unusable in this form, but the logic to calculate the actual index into the memory buffer is simple. In the above example, the head is at index 6 and the tail is at I believe every word you say, John. That's scary. The head is at index 6 and the tail is at index 2. Since we have a capacity of 9, to calculate the actual index, maybe we should say, yeah. From, how do I want to say this? We could say offset instead of index. Like they offset in the buffer. Okay, so here we go. In the above example, the head is at index 6 and the tail is at index 2. However, from a user's perspective, this is the sentence I'm missing. The head is at index 0 and the tail is at index 5. Yeah. Just like the array list above it. Since we have a capacity of 9 to calculate the actual index from the perceived index, we simply here we go. Let's get to that in a second. To calculate the index of the perceived index, we simply use modulo. Okay. Maybe pseudocode is still helpful here, which is to say, 5 modulo 9. Wait, I got this backwards, and no, that's fuck. What did I do? I got myself confused because I was thinking about too many things. Skill issues. Okay. In the above example, the head is at index 6 and the tail is at index 2. Yes, we know this much. We know this. Okay. We're so fucking good at this. However, from a user's perspective, the head dang it. The head is at index 0 and the tail is at index 5, just like the array list above it. To calculate the actual index from the perceived index, we simply use modulo. Yes, we're getting there. We're getting there. I'm so almost there. You have no idea. Why can't I figure this out right now? This is like the simplest part of the whole fucking thing. Oh no, I cursed again. The whole frickin' thing. The whole frickin' thing. Oh my god. I'm even doing it here. It's just the actual index modulo 17. Okay. Okay. We're really close. So oh, why am I having such a hard time with this? Am I just not thinking well? That's very possible. What is 5 modulo 9? It's 5. Of course it's 5. But is it? No, that doesn't make sense either. Oh no, what am I doing? I was literally just reading about this. But start is 0. Start plus offset. Okay, I'm gonna look at you guys. I was literally just reading this, and now I'm just gonna let chat bail me out right now. Oh, this is so annoying. This is like the basic part of a ring buffer. Oh god, live coding sucks so much sometimes. Okay, start plus offset modulo capacity. Oh right, because you need. I know what modulo does, John. I know what modulo does. I just was having an aneurysm. Okay, head is at index 6. So to get in, that's the whole point. That's the whole point. We simply use modulo. So the point is that we'd have 6 plus 5 modulo 11. Modulo 9. Yeah, so mod 11 modulo 9 is 2. Fuck. I can't not curse apparently. Not when I'm this annoyed with myself. Oh, wow. That was a lot. Okay, sorry about that everybody. And to calculate the actual index from the perceived index, we simply use modulo. Now, I know we use modulo, I just, didn't remember how we have that. Okay. Tail is at index 5, just like the array list above it. To calculate the actual index from the perceived index, we simply use modulo. Yes, we're so good at this. Which is to say that we say 6 plus 5 equals, right now, modulo 9. Okay, here we go. I think what I want to do is do this, and we would say head plus offset equals. Okay. So let's not use that one. Maybe we just do 4. So if we said something like ring buffer 4 equals head plus offset. Hey, Allison, how's it going? Head plus offset modulo capacity. Okay. Ring buffer 4. Okay, how about that? That's a little bit better. Ring buffer offset equals head plus offset modulo capacity. All right, very good. All right, let's see. All right, to calculate the actual index from the perceived index, we simply use modulo. I think this is nice. We can similarly calculate the tail if we, with the length, we can similarly calculate the tail. Here, the length is the length of our example using length. Visibly, the number of actual elements that have been, that are written. Sure. No, that's not exactly true. Does everybody know what length means? Okay. We can similarly calculate the tail using length. Lee Gade. Thanks for the follow. Okay. Tail equals head plus length minus 1 it's the other side modulo capacity. Size of the buffer. Yeah, the ring buffer, right? Not the memory allocation, but the buffer, right? Difference between capacity and length. Yeah. Quantity of non-null values of buffer is less than capacity. Yeah. Okay, I like that. Is that index 5, just like the array list above it. Let me think. Let me see how it flows with this. I think I did it this way because the way it flows with this paragraph. One base indexing is just superior. I know. We don't have to do length minus 1, right? But of course, then our modulo behavior would be a little bit more annoying. It may seem unusable in this form, but the logic to calculate the actual index into the memory buffer is simple. In the above example, the head is at index 6 and the tail is at index 2. However, from a user's perspective, the head is at index 0 and the tail is at index 5, just like the array list above it. To calculate the actual index from the perceived index, we simply use modulo. Ring buffer offset equals head plus offset percent capacity. I said percent. Modulo capacity. We can similarly calculate the tail. Yeah, I think I did it because of the way it was. I think it was just because of the way it flowed. But it was a good thought. Okay. We can similarly calculate the tail using length. Tail equals head plus length minus 1% capacity. Should I say something here? Maybe this is where the comment is helpful. Which is to say 6 accessing element 4. Oh shit. I'm just trying to decide if I should put it in prose or in the code example. E.g. accessing element 4. Maybe it's just better to do this. Ring buffer 4 equals 6 is our head plus 4 modulo 9 in our above example. Accessing the 4th index in our above example. Ring buffer 4 equals 6 plus 4 modulo 9, which outputs wait, I messed up, didn't I? 10 modulo 9 outputs 1. Oh, right. No, the fourth element is the fourth element is oh god, one based indexing again. 0, 1, 2, 3, 4. Yeah. Accessing the fourth index in our above example would give us 1. Accessing the fourth index, the value 5 in our above example, ring buffer 4 equals 6 plus 4 modulo 9 is 1. Okay. Oh god. Thinking. It's not the easiest thing. We can similarly calculate the tail using length. Which is to say tail equals 6 plus 6 minus 1 modulo 9, which, assuming we did this right, would be 11, which will give us 2. Index 2. That's our tail. Okay. I think that's good enough. Because index is pointer to element. Yeah. Accessing the fourth element in the value 5 in our above example. Yeah, no, that's good. I like that, John. Suyash. Yeah, writing a little article / blog. Little bit of both. I don't know. It just goes on my Substack. Okay, and then we just go right into what happens when it fills up. I think that's the obvious thing that we're wondering about. What happens when it fills up? Okay. It wraps around. Okay. Here is and finally the implementation of ring buffer with I don't actually know which methods I actually want to do. With pushback. I think I just want to do pushback and pop front. Oh god, I'm writing markdown again. With pushback, pop front, and an index trait implementation. I think the index trait implementation is nice. The implementation of ring buffer with pushback, pop front, and an index trait implementation. Is there anything else I want to do on the ring buffer? I like to try to like pre-think this a little bit. Ring buffer implementation, pushback, pop front, and an index trait implementation. Yeah, I think that's good. The only thing that's weird about having a fixed size ring buffer that allows overwrites is that essentially, let me think about this. Well, it's really only the case if the reason you're using a ring buffer is this sort of thing. And if you are using a ring buffer for this sort of thing, where you have two different processes, one that's reading and one that's writing, then allowing overwrites feels like it would be difficult to me. That's a half-formed thought. We'll see what happens. We'll see what happens in my head later on. Okay, let's write a summary and then we'll be good. Okay. Now with our ring buffer written, we have an array-based FIFO. We have a data structure. Yeah. We have an array-based FIFO queue. Yeah, we'll just say that. Now with our ring buffer written, we have an array-based FIFO queue. Overcoming the challenges of ArrayList from the last article. Okay. I think this is good. And I actually don't know what I want to do next. No, I actually am going to go on a vacation in July. It's possible. It's possible I am not streaming at all in July. It's possible. I'm going on vacay. So what do I really want to do next? I guess we could just do Do I want to get into trees before my vacation? That's really the question. Binary search tree is going to be, to me, one of the harder ones to fit into a single stream, at least for writing it in Rust. Maybe now that we did all of these sorts of structures, doing some sorting algos next would be good. Bubble sort and quick sort. We could probably do that. I forgot that I was actually going to do that before I wrote a ring buffer, because it's not like I'm going to sort a ring buffer. But I guess I set it up the way I did because I decided to do the whole queue and stack article, and a ring buffer just seemed like the natural next step for that. Let's see. So let's go into another article, copy the same lines I always say. The source code here, all of this malarkey. Next time we will implement sorting algorithms, quick sort, and bubble sort. For array list. Okay. I'm going to do those just on my array list. Next time we will implement quick sort and bubble sort for array list. Yeah, I like that. The source code with tests is available on GitHub. This is going to be the wrong link. So this needs to say ring buffer.rs. Let me make sure that I didn't screw that up. Nope, we're good. Now with our ring buffer written, we have an array-based FIFO queue overcoming the challenges of array list from the last article. Okay, I like that. And then is there anything else? Ring buffer is something you'll like. I'm not going to write this sentence. I don't like this sentence. Okay. I just want to say that there's a lot of use cases. So there's a lot of data structures that we write just because we write them, right? Like a singly linked list. What are you going to really use a singly linked list for? Not a whole lot. But like ring buffers are insanely useful and have a lot of applications. Maybe that's all I want to say. Sometimes the algorithms and data structures we write and study don't have a lot of practical application. But ring buffer is definitely an exception. With broad applications across programming disciplines. Okay. I think that's good. Cool. I like that. We'll write the code next time. I think this article's good enough. Overcoming perfectionism here, live on Twitch. Thanks for watching, YouTube. See ya.